here is familiar with any of Dungeons and Dragons or any of the games that are based on the D20 system, such as the Baldur's Gate or Neverwinter Nights series of video games? That would be the next poll. Yeah.
Apparently I missed this poll too, so if everybody could just
Missed
put
this one too?
a check mark or an X. I don't know how I missed it.
Yeah. Yep. Wow, not too many role players here. I'm a little bit surprised, because role playing is very much about probabilities, especially Dungeons and Dragons, which is very combat heavy. So the basic idea in role-playing games like this is that the core loop, the core activity is that you're gaining experience points. You're going out and you're completing challenges of some kind, and those challenges give you experience points. And when you collect enough experience points, then you gain a level. And gaining levels is a big deal. It gives you more power. It gives you more options in the game. So in general, a typical thing is you've got this experience point curve where you need, so in the D20 system, for example, you start at level 1, and when you collect 1,000 experience points, then you reach level 2. And then when you get 2,000 experience points on top of that, so 3,000 total, then you reach level 3, then 3,000 more to reach level 4, and so on. So this is just a graph of experience points to levels. And really in the game, it's not a smooth curve like this. It's actually a step function, because if you only gain a level at certain thresholds. You don't really have half levels. But we can also model it as a quadratic, and it's a little bit simpler for that. So you might ask a question that a game designer might ask is, well, how much playing time does it take to raise a level? You want people to be to remain interested in the game. You don't want them to feel like they're putting lots and lots and lots of time into the game and not really getting any kind of in-game reward. So so you might ask, well, if you're receiving experience points at a constant rate that never changes, then it's pretty clear that you will raise a level pretty quickly early on, and then it will get progressively slower and slower and slower as time goes on, and eventually it will become just unacceptably slow to the point where players will give up. They'll feel like they'll never get to the next thing. So clearly a linear XP gain is probably not the best thing. And in practice, experience points are usually on an increasing curve. So as you get, which makes sense also because as you get more powerful, you can take on greater challenges, and those challenges provide greater rewards in terms of experience. So just for simplicity, if we suppose that we had this progression over time that follows the same triangular curve, we get quadratically more experience per unit time the further in the game we go. Then, so let's say, for example, that at the start of the game you earn about 50 experience points per minute, and then 20 minutes after that you get 100 experience per minute, and 20 minutes after that you get 150, and so on. So it's basically the same curve as the experience points to levels, just a multiple of that, so that you would. And you might ask, well, how fast does the player level up over time given these two things? And could you graph that? And of course, the answer is you can. And since they're both the same thing, it would be the rate of level gain per unit time would be a constant. In this case, it would be 20 minutes per level. So okay, the next question would be for a game designer. Okay, maybe you don't want it to be constant. Maybe you want the curve to look like a very slight increase. So maybe you start with 20 minutes to gain your first level, and then maybe 22 minutes to reach the next level, and 24.2 minutes, maybe a 10% increase in time per level, or maybe a 25% increase or whatever. And so now you might ask, well, if we want to keep the triangular number curve for experience points required to level, and we want a given time curve of how often you level, then how often you reach new levels, then you need to figure out, well, what is the XP gained per unit time curve going to look like? So this is kind of an interesting math problem, because the interesting thing is you're not just plugging and chugging. This is a system of equations, and you could even make it a simpler system by making these into linear functions. Um, and you're not just talking about one equation, you're talking about relationships between several equations and several graphs. And the really interesting thing here is that you're not just given a system of equations and then plugging and chugging to solve it. Instead, you're given one equation, and then you're given the solution to a system, and you have to work backwards to find the right equation, the right missing equations to fit the solution that you want. So speaking of systems of equations, one of my favorite applications in math is the use of systems of equations to solve what designers call intransitive games. And the rest of us call it things that are like rock, paper, scissors. So this is a really neat math trick as a way that you can figure out what players will do if you give them a certain kind of intransitive system. So intransitive mechanics, where you've got different options, and none of them beat everything. All of them have some strengths and some weaknesses. They find their way into all kinds of games, and I could give tons of examples. But one really interesting space of this is what's called real-time strategy games, such as the recent StarCraft 2 that probably a lot of your students are playing heavily right now. So here's a very simplified example from a game like that, and I'm curious if anyone out there is a real-time strategy game player. So, Warcraft, StarCraft, a bunch of other games. And for those of you who haven't played real-time strategy games, basically the general idea behind these is that you have kind of a few interlocking systems, but mostly you have some kind of resource production. Okay. So mostly you have some kind of resource production, and then you use those resources to build combat units. You can close this now, Maria. Thanks. You use the resources that you've generated to build combat units, and you send those combat units over to your opponents in order to do combat with their combat units. So this is a very, very simplified example from this, but there's lots of cases where in real-time strategy games where you have these kind of intransitive things. So let's say a very simple example, and a very common one from a lot of real-time strategy games, is that you have 3 units that are each strong against one of the others and weak against the third. So for example, you might have infantry, which are strong against archers, and archers, which are strong against flying units, and flying units, which are strong against infantry. So for simplicity, we'll just say that if you build an infantry unit and you send it out against an archer, for example, they just completely slaughter the other unit. There's no they don't take any damage or any losses in exchange. You can actually solve this problem with partial damage too, where you'll even if you fight against the thing that you're weak against, you still get to take them down a little bit. But that's a little more complicated. So we'll just assume total losses here. So I'm going to build 1 unit, you're going to build 1 unit, and then we'll send them against each other, sight unseen. And we just have the series of these things until one of us runs out of resources. And let's assume that these things have different costs. So for example, we'll say that archers cost 75 gold, flying units cost 100 gold, and our infantry units, our knights, will cost 50 gold. And with this information alone, we can actually set up a system of equations to solve for an optimal percentage mix of an army. So if I asked you, here's 650 gold, what units would you buy? In what proportions? We can actually solve for that. And the way you do it is you first construct a set of 3 equations that say for each unit type, for each unit type, what is the net gain or loss relative to my opponent if they choose a different type? So for example, if I pay 50 gold for a knight and my opponent pays 75 gold for an archer, I'm going to win that battle, and my opponent has lost 75 gold worth of units. I've lost nothing since I can reuse my infantry, so I basically have a net gain of 75 gold compared to my opponent. So we can construct this table or a matrix of payoffs for the different outcomes. And from this I can construct a set of 3 equations of expected payoffs based on the probabilities that my opponent is going to choose a given unit. So the capital letters on the left side of these equations are my payoffs for choosing a knight, an archer, or a flying unit. And the lowercase variables on the right are the probabilities from 0 to 1 that my opponent is going to choose a knight, an archer, or a flying unit. So for example, the very first equation just basically says that if my opponent chooses an archer, I get a payoff of 75. If my opponent uses a flyer, then I get a negative payoff of 50 because they won. If I choose a knight, and you just multiply the payoff by the probability. If that's too advanced for your class, you can just do that part for them and supply it. So we've got this set of 6 unknowns and 3 equations. Well, that's not good enough, right? But since we're talking about a repeated set of trials, we know that all of these payoffs will eventually reach some kind of equilibrium point. That is, they'll all be equivalent to each other. If one of them had a better payoff, then you would just pick that more frequently, and then your opponent would pick other things more frequently to punish you for that until you eventually reach this equilibrium point where all 3 payoffs are the same. And in fact, since this is a zero-sum game, that is, you gain exactly as much as your opponent loses and vice versa, we know in fact that all those net payoffs are going to be 0. So now we have 3 equations and 3 unknowns, and we can solve them. Okay, I lied. So these 3 equations actually have some redundancy in them if you look at this very carefully. So they actually reduce to only 2 equations. Luckily, we also know that that the lowercase f, a, and k variables are probabilities, so they're all between 0 and 1, and since my opponent has to pick one of the 3 exactly, they all have to add up to 1. So there's our third equation, and then we can use substitution to solve, and we actually get these numbers here. So we would say that in this case, we would expect that 4 out of 9 times any given player is going to choose a knight, 2 out of 9 times they choose an archer, and 1 out of 3 times, or 3 out of 9, they would choose a flying unit, and that ends up being this solution. So you could phrase this in many different ways in a math problem. Like you could ask, given this cost analysis, what is the best or worst unit to choose, or which one do you expect to have the most or least frequent usage? You could say if you had 650 gold, which happens to be the cost of 4 infantry, 3 flyers, and 2 archers, how would you spend it optimally? You could say if in terms of optimal play, what is the ratio of archers to knights that you would expect to see in a game? And if you use computers, you can even put this and if you use computers, you could even put this into Excel and have it automatically calculate these ratios for you. So you could ask your students to construct these formulas and then use the spreadsheet to answer additional questions through trial and error. Like, what effect does it have on the frequency of flyers if you reduce their cost? Or if you increase the cost of archers, what happens to the frequency of knights? Or if you wanted to reverse the ratios so that archers were chosen 4 out of 9 times and infantry were 2 out of 9, but you were only allowed to change the cost of archers and flyers, then what new costs would you choose to get the ratio that you want? These are exactly the kinds of calculations that real-time strategy game designers have to do in order to figure out what the right costs are in order to balance their game. So now I'm sure, as you can tell, there's many ways to solve something like this. I mean, I did it here by hand with a system of equations and just variable substitution, but you could just as easily, if you teach linear algebra, put this into a matrix and then have the students put the matrix in triangular form and use back substitution. So there's a lot of different ways to do this. So finally, I want to close really quickly with an example. It's more from the programming side of things, but it's a really interesting set of problems that require geometry and trigonometry and algebra all together to solve, and it's something that's found in most games. And it's called collision detection.